without imposing any of the conservation laws. So we'll have that will have d3k divided by 2 pi cubed. 1 over 2 EP, 2 E K. And then, let's see, 2 pi to the 4. And then the delta function that expresses the conservation law. So P plus K should be equal to the initial momentum, which is 0. So this is a 3-dimensional delta function. And then there is 1-dimensional delta function for the energy conservation. Yes?
Why do you have an integral here when you didn't have an integral?
Very good. So let's let's compute the full gamma. That's an integral. So the full gamma is defined by an integral of partial decay, of differential decay width over the available phase space. So let's integrate. Let's take this formula. So there we have the integrals. But we should also multiply by the matrix element. And divide by 2m. So now, okay, so we eliminate the delta functions just one by one. So first we look at this delta function. So this delta function tells us that k is equal to minus p. And so we should just substitute k we should substitute minus p for k wherever it appears. And where does it appear? Well, it totally appears here. So the matrix element itself will only depend on or whatever there is, we replace. So in the calculation of the matrix element, the energy momentum conservation laws are already included, right? So this can only depend on one of the particles' energy and momentum. So anyway, we can just write this as d3 p over 2 pi cubed. So here we substitute minus p for k. Yes?
In the second delta, the energy delta, the p squared and the k squared, there's some bars over them for 3 momenta?
Yeah, this is 3 momenta.
Thank you.
So let's see. So out of this 2 pi to the 4, 3 2 pi's canceled these 3 2 pi's. So we are left with 2 pi times delta mp squared plus m squared times 2 and then minus m. And then we also have the matrix element squared. So now I eliminate this delta function. So I can do another integration for free. Okay, so from these three integrations, one is fixed by the delta function. So I write my three-dimensional volume element in momentum space as p squared dp times the two-dimensional solid angle, as written in the picture above. So this will then be equal to integral over this solid angle then dp p squared divided by 2 pi squared. So this 1 2 pi is cancelled. So multiplied by 2e p squared. And then the delta function of 2 square root p squared plus m squared minus m. And then whatever is stands here. And now I use another delta function to integrate over the absolute value of momentum. So what's left is the angular integral. So there will be a factor of p squared divided by the energy squared. And then when I eliminate the delta function, I need to divide by the derivative of the argument with respect to the integration variable. So this will be d square root of pi squared plus m squared differentiated with respect to p. So let me check the factors of by the way, there is a factor of 2 missing in the formula. So you see this 2 was missing there. So anyway, the final result will be d2 omega divided by 32 pi squared. And then what's this integral? One can see that d energy, the derivative of energy over momentum is velocity. This is a general relativistic. Actually, it's not only general relativistic equation, it's very general definition of what is velocity. So the group velocity is the derivative of energy with respect to momentum. So for a relativistic particle, velocity is momentum divided by energy, which you also obtain from here by their differentiation very easily. So this cancels 1 power of p and 1 power of e. So we're left with this expression. Now, in this particular case, we can even integrate over the omega because certainly it doesn't depend on which direction the particles fly, right? So we just multiply the total result by 4 pi, and that's it. Yes?
Sorry, did you just say that you've missed a factor 2 in the previous phase differential
I
calculus?
think so. Yes, there is a... There is a factor of 2 missing, right? So this 2 should appear here. So the correct answer is 1 over 32 pi squared.
So in the last result, the b is evaluated at the b is function of the big M and the right? The way that the value where the delta function here.
Yes, P and E are related, of course. They are. Any more questions? Yes.
Are we calculating d of gamma 1 to 2, d gamma, or just gamma?
That's gamma, right? So we are integrating over.
Okay, because I want to use this formula over here that you boxed. If you say d gamma is equal to d phi times your amplitude factor, then
That's the integrand here, okay? So this I would call d gamma. And I need to integrate it over the remaining phase space. So the idea here that we use all the conservation laws, which are trivially imposed. And so the remaining integral, we call the phase space integral.
right. I'm just saying that if you look at that integral right underneath the momentum arrow things,
Yes?
then and I compare it directly to the equation for d phi at the very top, then it looks like it should be d phi times your amplitude factor, and that would mean that what you calculated was d gamma, not gamma. Just by comparison.
Say again, please.
Okay, sorry.
Sorry, I think what he's trying to say is that there shouldn't be an integral sign on the right side of the d phi equation there.
Yeah, should that be without an integral?
Because
yes, and right, yes.
So there's no integral at the top over there.
But then how does the three-dimensional integral becomes two-dimensional?
Okay, my only reservation
So-
is just because of this formula
Yeah.
over here.
It's just when you take the expression here at the top, and you just plug it into that formula over there. That's in the box. You will get that result. You just got this d gamma, not gamma. It's this formula when you take that formula on the top and plug it in. This something. Missing something.
So well, what should I say? So in this formula, let's decide on convention. So in this formula, d phi means this. So then, right, so the formula for d gamma would then be this thing. With the matrix element. So this would be d gamma.
Without the integral.
The,
Yeah. So on the very top, the formula on the very top shouldn't have an integral. On
Yeah.
the very top, on the top board.
hold on. So then we want to. So the idea is then that we can always trivially remove 4 out of these 6 integrals by using delta functions. So you can just integrate for free. So that's what this integral there signifies. So in principle here we should write 6 integrals. And there we do 4 of them. So, and that is independent of this matrix element, of course. This is just the use of the this is just the use of the conservation law. So, I guess in the literature, both this thing is called d gamma and this is called d gamma. But I mean, you can always reduce that d gamma to this one by using conservation laws. Is it still confusing? Yes.
So, to be clear, so either we don't integrate over phi until we have the full formula, or we integrate the 4 integrals beforehand, and just afterwards, when we look at gamma, just require momentum conservation in the formula for the m.
Exactly, yes. So this is just a generic formula that's valid for the integral for the decay to n particles, and can be anything. Now this is a simplified formula that's valid for 2 particles, where we can use momentum and energy conservation to just eliminate the 4 integration variables. So then what do we do next? Well, we can compute the total width of decay into n particles. So this is called partial decay width. The total decay width is equal to sum of overall channels. So this typically a particle can decay into, I mean, if you say consider some unstable particle, it may have different decay channels, and so the probability of decaying into some particular final state would be given by the partial decay width, and the particle's lifetime is given by, so they are added in, like probabilities are added in quadratures, right? So the decay width are added linearly, and so the total probability is characterized by some overall channels. So let's now consider the next case. Namely, we consider the case where we have 2 particles in the initial state. And that corresponds to scattering. So scattering can be either elastic or inelastic. So when we have the same particles in initial and final states, that's called elastic scattering. So they just, the particle, there is a target particle and there is a projectile, and so projectile just is deflected by the target over some angle. So this would be an elastic process. Now, inelastic scattering corresponds to some particle production taking place. So, for instance, we collide, I don't know, 2 electrons, and out come 2 muons. So, in the process, there is some change of internal structure of the particles. So, this is then called inelastic process. We can consider them both on the same footing here, well, we need to understand how to characterize the probability of the scattering process. So let's first study the classical picture of what we really want to compute. So, well, for that, let's sort of make a schematic simplified model of scattering between particles. So let's assume that we have some target that consists of particles that we will model by rigid spheres. Okay? So let's call this particles B. We will assume that they are distributed with density NB. So there is NB particles in unit volume. And our hard spheres of radius that will denote by RB. And then there is some incident flux of A particles. So A particles we assume to be point-like, and they only interact with B particles when they collide head-on. So they behave like billiard balls. So they only interact when they really hit a B particle in the strict mechanical sense of this word. So the question is how many. So suppose that the particles A are sent in by, say, short pulses of some duration t, and then they move with some velocity v. So they have velocity va. So this is completely non-relativistic now. The question is how many collisions will there be? Which, of course, we can easily figure out how many collisions will happen. So suppose that the cross section of this bunch of particles is let's say it's just a round pulse. It has a circular cross-section. And so these particles are distributed with some density, which you also know. Then what will happen? So we just well, look how, so when we move this so when this pulse moves through the target, in a sense, these particles will drill holes in this in this flux. And so if you project them into the cross-section, the fraction of the A particles deflected, so the A particles that will undergo collision are those that are sort of lie in the shadow of the B particles, right? It's just, well, a geometric way of characterize what's going on. So the number of collisions then will obviously be proportional to number of incident particles, and the fraction of incident particles that will experience collisions is equal to the fraction of the shadowed area to the total cross section of the bunch. Right, so this will be equal to what? To total number of B particles. And so each B particle occupies an area equal to, we'll call it sigma B, but sigma B is simply pi r B squared. So this is the size of the B particle. And then we should divide by the the total area of the bunch, the cross section of this incoming part of this flux of particles. But what we really want to, I mean, it of course means that, so if you increase the length of the pulse or the cross section, of course the number of collisions will increase. So a correct sort of intensive measure of the number of collisions will be the number normalized to the unit volume and to the unit time. So So then we need to divide by the volume and by time. And so this will be equal to NA times NB times sigma B divided by V times T times A. So this ratio is equal to just the density of B particles. Now T times A can also be expressed as the volume, because we can write this as we can express this as the length of the bunch measured in centimeters. I guess divided by velocity, right? So the time length of the bunch will be equal to the spatial length divided by the velocity. And so finally, we obtain that the number of collisions per unit volume per unit time is equal to proportional to the number densities of particles, velocity of times velocity of the incident particles, and times the size of the particles in the target. So, in a sense, this factor is just kinematics. It's boundary conditions, if you wish. So this is given by particular setup that we are considering. So what characterizes the collisions themselves is this quantity. So in general, if we consider a very simple model of interactions, so these particles B behave as black disks for particles A. If we consider the more general situation, the quantity that would characterize interactions between A and B will be something of dimension of area, and this is called the effective cross-section. So in general, two particle collisions are characterized by the cross section. So in a sense, this the cross section defines what transverse size. So if you have particles A, how big particles B will look for them. So the way to calculate the scattering cross-section is through this formula. So so this is the probabilistic measure of the number of collisions. It's a probability right? So it will be equal to the number of events happening in unit volume per unit time. That's something that we can calculate using quantum mechanical rules. So then after extracting this kinematical factor, what we'll get is the effective cross-section. Right. So to calculate the probability, we we have to multiply the phase space by. So this is, we are now considering a process in which two particles collide and produce n particles. Then we should integrate over all possible moment of final particles with the measure dictated by the way we normalize the states. Then we should take the square of the matrix element. And so let the momenta of the incoming particles be Ka and Kb. So we have particles with momentum Ka and Kb colliding with each other. So that has to be normalized by the norms of their wave functions. And so this would define us the probability. So again, we substitute here the expression with the delta function. And yes,
Maybe a square.
should be a square. That's right. So what do we get? Well, so we get this will combine with the delta function coming from the matrix element to the phase space times the reduced matrix element squared. And then there will be a bunch of factors that come from normalization. So each of these norms will give a factor of energy. And then we will have, okay, so here, from here we'll get the volume of space-time. And in the denominator, we will get a factor of volume squared. Right, because each of this is volume normalized, each of the wave functions. Now, if we compare this to the formula on the top of the blackboard, then we will see that the number of collisions, so probability, what is probability? It is the number of collisions divided by number of A and B particles. So probability divided by volume divided by volume and time will be equal to the number of collisions so for the number of collisions divided by A and then B, we get what? We get the velocity times the cross section, and then divided by volume squared. Right? So here we use just, this is the kinematical relationship. This is, if you wish, this is a definition of what we call the cross section, because it appears precisely in this way in the formula that we got over there. Right, so then probability we can calculate, so we should divide it by volume and by t, and what we should get is sigma times velocity divided by volume squared. And this is precisely what we get here. So without these infinite factors, what stands here is the differential probability, but times the relative velocity of particles. So we thus find for the differential cross-section the following formula. So it will be equal to the phase space times the matrix element squared, and then divided by by 4 times the energy of the A particle times the energy of the B particle, and divided by their relative velocity. Well, strictly speaking, this formula is valid in the rest frame of B. Right? This is because all our arguments were given in the rest frame where we considered, so in the frame where we considered some particles as a target and the other particles as projectile. And of course, physics is Lorentz invariant, so we should be able to write this in general frame. So this formula should be Lorentz invariant. So the claim is that in any frame, what we should use for this product is a manifestly Lorentz invariant expression. So I leave you as a home exercise to prove that this equality holds in the rest frame of B. So if you set the three momentum of B particles to 0, you should be able to see that the left-hand side is there will be the velocity of A particles times their energy times the mass of the B particles. And so it should be understood that in the denominator in this formula we have this square root. Then this formula will be valid in any reference frame. Yes?
Sorry, is that the dot product of the four momenta?
So here, yes, this is a product of four momenta. So it's manifestly Lorentz invariant. So you can prove this, and the other statement that you can prove is that if Ka is and Kb are collinear, these are three momenta now, so that collision is head-on. Then the relative velocity, well, is the usual, and this is the obvious. So we get the expected expression for relative velocity, just the difference between velocities of A and B taken in absolute value. So all right, then we get the formula for differential cross-section. In any reference frame, it's written as can be written through the Lorentz invariant quantities. So the phase space is Lorentz invariant. This is also Lorentz invariant. So this cross section, in fact, is Lorentz invariant. Now, if you want to compute the total cross section, we just integrate over the phase space and sum over all possible channels of the reaction. So on the next lecture, we will actually apply this to the simplest process in quantum electrodynamics, namely to production of muon pairs in E plus and minus collisions. Yes?
Will the values of the sigma and the amplitude not depend on the frame? I mean, if you change the frame, you change the momentum, and then you...
No, M is calculated from Feynman diagrams. Feynman rules are Lorentz invariant.
But the input is the momentum of the particles, right? Which changes.
So affine rules are formulated in terms of 4 momenta. So whatever you get out from them will be Lorentz invariant. Can depend on momenta of external particles, but in such a way that it only products of 4 momenta appear. So each single, so then this is Lorentz invariant and this is Lorentz invariant. Therefore, the left-hand side must be Lorentz invariant. Yes?
I'm trying to see how you go from the expression B to integrate. So do you simply replace the VA by B ability?
Yes, absolutely. So,
Do you replace
so this is the logic here is following. So we right. So what we get here would fit with our simplified picture in the frame where B were at rest. Now the crucial step here is to notice that the expression, this square root expression, would reduce to V times C times E in that frame. And therefore, it's the correct definition of the relative velocity in any frame. So in particular, in the frame where the 4 momenta are collinear, the relative velocity is literally the difference between velocities. But if you go in the frame where they are sort of collide at the angle, then you have to use a more general relativistic expression. Okay, I guess I'll stop here. Thank you, and then see you tomorrow.